Alrighty, folks, let's do it. We're continuing on section 3.6. First of all, does anyone need that? A couple of you were absent last time, so perhaps you need section 3.6. Anyone want a copy? Here you go. Anyone else need another copy? I have lots of extra copies. Allison, you have one?
Yeah.
Okay. Alrighty, folks. So we were talking about how do you find the area between two curves. That's an exciting question because it finally allows us to answer the original question, how do you find the area of a blobby blob or of a curvy shape? And so I have two functions here, f of x and g of x, and I'd like to know the total area between them. I can find that area by doing an integral, and we simply calculate the integral of the top curve minus the bottom curve. And that's a very powerful idea because any shape that you can create between two functions, you can now find the area of that shape. And then how do you find the volume of a solid of revolution? So we were talking about what if you had a shape, maybe a parabola, and I take that shape and I allow it to rotate in and out of the board, creating a three-dimensional figure that would look something like this. We can now calculate the volume of that figure. That's fascinating because we're going from two-dimensional quantity up to a three-dimensional quantity. So now you can calculate the volume of such a shape by doing pi f of x squared, where f of x is whatever function that you want, and then you rotate it around the x-axis and create a three-dimensional figure, and now you know the volume. So those were the two formulas we talked about last time. Today is November 21st. We are going to wrap up 3.6 and maybe start 3.7. What else? Next time, on Monday, we'll finish 3.7, and then Wednesday, we'll review for your next test. Then on Monday, December 3rd, you'll take your last test, your last chapter test in this class. And then the next day, we'll have a review, and then finally, you have your final exam. Okay, and I did the nacho cheese joke with you last time. Yeah, so did you hear about the two guys who stole a calendar? They each got 6 months. All right, it's kind of a math joke. Okay, we finished off on number 7. This is the last problem we did, number 7. We didn't exactly finish it. So just for the sake of everybody feeling good about this formula for the volume of a three-dimensional solid of revolution, let's see again how that worked out. Your function, even though they say y, you can rewrite that as f of x. So your function is e to the 2x plus 4. And so we want to take this integral from 0 to 0.5. I'll go and bring my pi outside of e to the 2x plus 4 squared. Now looking at that squared term, you might temporarily think, oh no, what do I do? Do I have to do integration by parts? Do I have to do u substitution? And in this particular case, you can actually just FOIL that out. That's nice. When that exponent is small enough, you can just FOIL it out. Now look, had that exponent been 25, okay, no, you wouldn't want to FOIL that out. You could, it would just take a really, really long time to do all that FOIL. But since it's just squared, that's pretty simple. We can FOIL that out. So what did we get? We got 0.5. FOILing that out was e to the 4x plus 8 e to the 2x plus 16. Is that correct? Is that what we got?
Yeah.
Okay. So now we go ahead and do the integral. This integral is fairly simple to compute. You might want to remind yourself that that 16 is actually 16x to the 0. And remind yourself how to do the integral of e to the nx. Anytime you take the integral of e to the nx, it's simply 1 over n e to the nx. So you divide by the number in the exponent. So we have 1/4 e to the 4x plus 8 over 2 e to the 2x plus, this is just an anti-power rule, add 1, divide by what you get, that's 16 over 1 x to the first. Now folks, you notice how I wrote 8 over 2 and 16 over 1, even though that's painfully obvious that that's a 4 and that that's a 16. That's true, but see, it's helped not to erase the tracks of your work. It's helpful to be able to go back and say, oh yeah, how did I get 4? It's because it was really 8 divided by 2. And how did I get 16? Because I was really 16 over 1. It's helpful to write it down that way once, and then go through and simplify. So now you say, okay, 1/4 e to the 4x plus 4 e to the 2x plus 16x. It just helps to make sure that you're not going to make a mistake. So we're evaluating that from 0.5, and don't forget that there's a pi up front. So now we get to do parenthesis minus parenthesis. So pi outside of parenthesis minus parenthesis. When I plug in 0.5, that's going to be a painful 1/4 e to the 4 times a half is 2, plus 4 times e to the 2 times a half is 1, plus 16 times a half is 8. So that's the first part. And then minus, plug in a 0. E to the 0 is 1, so that's just 1/4, plus e to the 0 is 1, so that's a 4. And then 0 times 16 is 0, so that's just 1/4 plus 4. So now we have that. And that all gets multiplied by pi. I think the last thing we could really do is leave the e squared term, leave the e term, but we can do 8 minus 1/4 minus 4. So what does that leave us? Pi times 1/4 e squared plus 4e. And then 8 minus 4 is 4, minus 1/4 is 3.75. Okay, did you all get that as your final simplified answer? Of course, that's not a decimal yet. We would still want to do the decimal. Now let's review some clever tricks we learned last time. We can, of course, compute this integral on Desmos, because Desmos will compute any definite integral. So I can type in my keyboard function miscellaneous integral from 0 to 0.5 of pi, which I think I can just write pi, and then the function e to the 2x plus 4 squared dx. It gives me 51.743. 51.743. Isn't that nice? Just by typing it into Desmos, you already get your answer. Now, what's my answer? My answer was pi times 0.25 e squared plus 4e plus 3.75. Oh, goody. Gives me the same exact answer, 51.743. So that's good. We know we have the right answer, but one last thing you might want to remind yourself is Wolfram alpha. Wolfram alpha. Does anyone know where they got that name, Wolfram alpha? I have no idea. Wolfram alpha. Now I can go ahead and type in, let me just go to Desmos and I'll steal that integral. I wonder if that'll let me just copy and paste it. That would be convenient. Oh no, that did not paste right. If that knows, oh my gosh, it knew it. Can you believe it, folks? Look at that gobbledygook. And yet it knew how to interpret that, and there it is, and it also gives me 51.743. And does it give the volume of revolution? No, but if I type it in, volume of revolution of e to the 2x plus 4 from 0 to 0.5. Seriously, folks, are you impressed by Wolfram alpha? I mean, just look at that simple, choppy English that I typed in. And yet, there it is, the very first line already told us 51.7433. And look, it even gives you a really nice three-dimensional image. Folks, that's really cool. You should jump up out of your chairs, slap the ceiling, and then sit back down again saying, yeah, wow, that's really impressive. I did not know that there were such computational engines out there. Okay, well, there we have it. Moving on, we're starting a new concept today, a couple concepts. The first one is the average value of a function. This is kind of neat. The average value of a function. This is something you could immediately ask about your bank account. Everyone think about your checking account. On any given day, what is the average amount of money you have in your checking account? Right? We would all have a different average value. Maybe your average value is $100. That's on average how much you have in your bank account. Or maybe your average value is $1,000. Maybe your average value is $0 because you don't even use your checking account. Maybe your average value is negative $20 because you're constantly overdrawing your checking account. Either way, we're asking the question, what's the average value of what you have in an account that's constantly going up, down, up, down, up, down, right? So just as a simple example, consider this function right here in Desmos. What if I just gave you the graph of y equals sine x plus 4? Folks, what's the average value of this bank account? There we go. There we go. What is the average value of this bank account? If somebody were to ask you and you wanted to give a reasonable answer. Oh gosh. Oh, there we go. Yeah, on average, how much money do you have in this bank account? Allison, what do you think? On average, how much money do you have in this bank account?
Let's see.
Yeah. I think 4 sounds good. Why did you choose 4?
Because it's between.
Yeah. Exactly right. Now, there's an interesting mathematical way that we actually define this idea of average amount. The average amount would be the imaginary line that you could draw, okay, such that the total amount of area, let's just go between 0 and 10. Okay, can we all just pretend that there's a 10 right there? The total amount of area underneath this dotted line should be equal to the total amount of area underneath the red curve. Okay? So, because first of all, if you wanted to know how much total area is below the red curve, you would find all the area here, below the red curve. And that would be what you could say the total amount of money in the bank account over those 10 days. But instead of your bank account fluctuating up and down, you would smoosh out that curvy line flat and say actually the amount of area here underneath that dotted line is the same as the amount of area that's underneath the red line. And then that dotted line we would call the average amount of money in the account. That's the actual definition. So even though your bank account is fluctuating at $4 up to $5, down to $4, down to $3, up to 4, up to 5, down to 4, down to 3, the average amount of money is that amount of money such that the area underneath that rectangle is the same as the area underneath your fluctuating curve. So we're equating those two areas and calling that dotted line the average amount. So everybody look at problem number 8. Where did that graph came from? Where did that graph come from? And number 8. Are you going to see that graph on the More website? Yeah, Alexis. That graph is not going to show up on the More website. Where did the graph come from? Well, yeah, it came from the function they gave me, and it's because I went to Desmos, graphed it, screenshotted it, and then pasted it onto your worksheet, okay? So if you want to see a graph like that, you have to go to Desmos and look at it. In any case, folks, go ahead and look. We're finding the average value of the function on the interval from 1 to 4. So go ahead and put a little tick mark at 1, and then put a tick mark at 4. And I want you to visualize and look at the amount of area under the curve right there. Now just think about how much area that is. Alexis, do you have packet 236? Let me get it. Sure. Now, folks, what I'd like you to imagine doing now is take that area and allow it to melt like water and sink down into the container. Okay, so like maybe this is your coffee cup on the way to work and you're sloshing it around and all the liquid is sloshing back and forth between the walls. These are the walls of the cup between 1 and 4. Let's pretend all of a sudden that that area is water and it can just sink back down under gravity and fill the cup with an even line. I want you to draw that dashed line, which you believe would be the level of water in this container if that graph of the area sank down like liquid. Does that make sense what I'm asking you to do? Pretend that that area is liquid and then it falls down to fill this cup or container from 1 to 4. Where would your level of water be? I'm just going to take a guess and put it around here. So that's 10, 20, 30, 40, 50. 10, 20, 50. I just made a guess. I'm going to guess that the average value is 43. I should guess 42 because it's the answer to the life, universe, and everything. But I'm going to guess 43. What did you all guess? Where did you put your dotted line? Josue?
It's the same line. I didn't guess 43. It's 40.
You guessed 40 exactly. Okay, perfect. So Josue put a dotted line right around 40. Let's see here. How about Allison? Where did you put your dotted line?
41.
Oh, 41. Very good. And Bata, where did you put your dotted line?
40.
40. Okay, I got that one. Michelle, where did you put your dotted line? 40 as well. Okay. And where did you put your dotted line, Efren?
50.
Oh, you did 50. That's just fine. That's totally fine. Hey, we can all be wrong. Okay, and what about you, Sada?
45.
Oh, 45. Very nice guess. Okay. And then how about you, Sela?
Put it a little lower.
A little lower than what?
A little lower. So put it
Oh, you put it at 30. Okay, that's fine. So 30. And then finally, Diego?
40.
40. And Steven, what'd you put it at?
47.
Oh, 47. Okay, very nice. Okay, well, folks, other than, who said 30 again? Sela? Other than Sela's outlier, which is fine, Sela. You could be right and we're all wrong. Just all of you let your eyes kind of go fuzzy and look at that line right there that I've drawn with all of your guesses. Would you all agree that the average value is somewhere around there? It's somewhere around there. If I turn that black area into water and let all the water fall down in the cup, it would probably be a water level of right around there. So now we just have to actually compute it. But that's the concept. That's the concept of what we're asking. So they gave us a formula, and the formula for the average value of a function is given by this. So the formula, let's write it all again in your own handwriting, is the integral from a to b of f of x dx. So that's simple enough. You're just doing a normal integral, except you're taking your limits of integration, a to b, and you're making a fraction out of 1 over b minus a. That's 1 over top minus bottom. Upper limit of integration minus the lower limit of integration. So add that to your list of formulas. We had a formula for the area between two curves. We have the formula for the volume of a three-dimensional figure. And now we have the formula for the average value of a function. So I'm going to write down average value is just 1 over b minus a, integral from a to b, f of x dx. Now, folks, I hope that you appreciate that these three formulas are not super crazy. The first formula, you just subtract two functions. This formula, all you do is write pi, and then you square the function. And then this formula, you're just doing the normal integral, but you're writing an extra fraction out front of 1 over b minus a. Okay, so let's do it. We're doing this integral from 1 to 4. The function is 6x squared. And therefore, the fraction out front will be 1 over 4 minus 1. Is everyone really excited? You're on the edge of your seat. You're like, oh boy, what's it going to be? Is it going to be 42? Is it going to be 30? Is it going to be 50? What is it going to be, Paza? Paza now changes his guess to 50. So we have 1/3 integral from 1 to, well, I can go ahead and do the integral now. So we have 1/3. The integral is simply the antiderivative, the anti-power rule. So add 1, divide by what you get. So we have 1/3 out front. That comes from the 1 over b minus a. I just did the anti-power rule for 6x squared. That became x cubed, 6 over 3. And we're going to integrate from 1 to 4. So I'm going to clean that up considerably. So 1/3 times 6/3 is really 6/9 x cubed from 1 to 4. But 6/9 is really 2/3. So that's 2/3 x cubed from 1 to 4. And now we can do our parenthesis minus parenthesis. So that's 2/3 4 cubed minus 2/3 1 cubed. Folks, just looking around the room at your work, I'm going to make an observation, and I hope you make the same observation. Aren't you impressed by what you're seeing on your paper? I mean, I'm not exactly calling it goodwill hunting, but to a lot of people, wouldn't it look like goodwill hunting? I mean, you're making some really good mathematical work on your paper. It looks really sophisticated. You walk into any party and show that work around, people will go, whoa, you're really sophisticated. You can do calculus. Like, the work you're doing is sophisticated. And yet, at the same time, is this really all that hard? It's actually not that hard. So what did we end up with? I didn't do the computation yet. Let me get my calculator. I got 2/3 times 4 cubed minus 2/3. Oh my gosh, it turned out to be the answer to life, the universe, and everything. 42. Should have guessed 42. Has anyone read The Hitchhiker's Guide to the Galaxy by Douglas Adams? That's where that comes from. Someone asked, what is the answer to life, the universe, and everything? And this supercomputer churned the question for for a long time, and the computer finally said, the answer is 42. Anyway, that's just kind of cult culture regarding the number 42. All right, well, we're all done, folks. So now if you draw in that line 42, the actual line 42, and then if you actually melted down that area would melt down and fill the cup at a level of 42. That's the average value. So here's another one. And this one is actually about money. Now, by the way, folks, have you heard the phrase average daily balance? Have any of you heard this? Average daily balance. So, wait, so have you? Anyone? Average daily balance? What does this refer to? Typically refers to credit cards. It can also refer to your checking account or your savings account, but more likely it refers to your credit cards. Because credit card companies, how often do they charge interest on your account? Monthly? Daily. Credit card companies charge interest on your balance daily. That is, if you hold a balance for more than a month. Because as you all know, so long as you pay your credit card off every single month, you never pay interest. And that's how you win the game. You win the game by always paying your credit card off every month. If you don't pay your credit card every month, then they charge you interest. And they go back retroactively and they charge you interest every single day for the money that you had on that credit card. And what do they calculate? Your average daily balance. So for every given day of the calendar month, they look at how much money you had spent on your credit card. So like, let's say that as of Monday, November 1st, I went ahead and I charged some money to Amazon, and I have $100 on my account now on November 1st. Then on Tuesday, November 2nd, I spent some money, more money on Amazon and other websites. I spent $50, and then I spent $20, and then I spent $30 more, and then I get a pizza, and then all sorts of other things. And so now I have spent, I already had spent 100. Now I've spent, oh, not that it matters, $240. So my average daily balance. Yeah, so on that particular day, I had a balance of 100. By that day, I had a balance of 240, and so on. I think they do something more than just that. They don't just look at how much you ended with at the end of the day. They're looking at your average daily balance. So they're going to take the balance of every day of the month and then divide it by 30 and see how much money you would spend on average each day. Anyway, it's brutal. Those credit card companies, they're going to do whatever they can to charge you interest. Okay, so back to the question. Suppose you deposit $4,000 at 3% interest compounded continuously. So this is you. You're investing $4,000. So everybody start by drawing a graph. Put a line at 4,000. And that's how much money you have in your account at time equals 0. Now what is this graph going to look like? It's the amount of money you have if you invested 3% compounded continuously. So first of all, is this going to be linear? Is it going to be a straight line? No. It's going to be compounded interest. And so just recall, compounded interest, if it's discrete compounded interest, then the formula is A equals P 1 plus R over N to the NT, where n is the number of times you get interest compounded. So if it's monthly, n is 12. But if it's compounded continuous, it's PE to the RT. So that's compounded interest, continuously, continuous compounded interest. So if we go ahead now and take a look at y equals, our principal was $4,000 times e to the power of an interest rate of 3% times x, which is time. That is our function. Let me zoom out. There it is. Wowzer. Now, I'm going to have to really adjust the scale on this. 4,000 e to the 0.03x. Well, that's the correct formula. Everyone, you can go ahead and jot it down. That's the correct formula. But I need to adjust my window to look out a ways. Oh, no, I don't need to look out a ways. I need to not look out so far. Oh, there we go. I need to only look out, like, say, as far as 10. And I need to increase my y-axis up to... Why is this not working? Why is it showing? Where to go from 0, 10. Ah, there we go. There we have it, folks. Now, again, I hope you noticed how long I had to fiddle with that window to make it look like something good. The thing is, what is time always in? What unit? Days, weeks, months? T is always in years. T is always years. So what we're looking at then is time is years, so I only wanted to bump time out to 2, 4, 6, 8, 10, something reasonable, you know. I don't need to bother making T more than, say, 50 or 100, right? Because we'll all be dead. We're just interested in our own lifespan. So how much interest am I going to get on this account? So I just looked at the next 10 years. I started at $4,000, and you know, reasonably speaking, if you're earning interest, you're only going to be looking at a couple $1,000s in interest. So that's how I knew how to choose my window. So everybody go ahead and make a picture of that. You've got your $4,000, and it is a compounded interest, so it's curvy, it's curving up. And that's what we're looking at. It says find the average value of your account during the first 4 years. So let's look. Year 1, year 2, year 3, year 4. Go ahead and put an ending point to it. So we're looking between year 0 and year 4. And you have a curvy line there. Now go ahead. Oh, and we can go ahead and compute how much money there is in the account at the end of year 4. At the end of year 4, it's oh, there we go, 4509. Actually, 4510. 4510. That's how much money you have. Okay. 4510. At the end of 4 years, you have $4,510. Now, how did I know 4,510? I looked it up on Desmos. But if I didn't want to look it up on Desmos, how would I do it? I would just put it in my formula. A equals 4,000 e to the 0.03 times the 4th year. And if you just put in 4 for t, this will give me that amount. So let's see. 4,000 e to the 0.12. Yeah, that came out to be 4,509.987, which is really 99. So a penny less than 4,510. So now, on your own paper, you have this nice graph now. Go ahead and put in your average value. If that area turned into liquid and it settled into the bottom of the cup, where would your average value line be? Now, why am I asking you to draw the average value line? Is it going to be accurate? No. But you're just reminding yourself the concept of what you're doing. You're going to draw a dotted line somewhere between 4,000 and 4,500. So at the end of the problem, when you're all done doing your integral, right, so we're about to do our average value integral, 1 over b minus a from a to b f of x dx. If you're all done doing your integral and you get 12,480, should you know right away you did it wrong? You should know really fast right away you did it wrong, right? Because you already know the concept. What should the answer be roughly?
Between those two numbers.
Yeah, go ahead and pick something.
$4,200.
4,200 sounds great. Once again, 42, the answer to life, universe, and everything. So yeah, I mean, you're expecting an answer around 4,200, 4,300. I mean, folks, really, truly, in any math class, in any math problem, you should be able to come up with a reasonable answer just off the cuff. Like, well, it's going to be around 4,200, 4,300. You should be close in the ballpark. Okay, so yeah, that answer would be wrong. Okay, well, folks, go ahead and do it. Plug all the information into your formula. Take your integral. We'll compare answers in a second. So your function f of x is the function we wrote down, 4,000 e to the 0.03t. Oh, I guess I never wrote that down anywhere, did I? I never wrote it down anywhere. The function that we did was f of x equals 4,000 e to the 0.03t. So that's your function that you're doing inside of your integral.
Is A 0?
Is what?
A 0.
Oh, yeah, really good point. So what's our a to b? Where are we integrating from? 0 to 4. So yeah, so far we have from 0 to 4 of 4,000 e to the 0.03t dt, or x dx. And with the fraction out front, 1 over 4 minus 0. And yeah, see, thank you. The limits of integration, a and b, are what we're interested in between the first 4 years of the bank account. So it is between 0 to 4. That's our limits of integration. So they're 1/4, and then we're taking the integral, 4,000 e to the 0.03t. So remind ourselves, how do you take the integral of e to the nt? I had it over here and I already erased it. But the integral of e to the nt is 1 over n, e to the nt. So to take the integral of e to the nt, you're simply dividing by the number in the exponent. And the number in the exponent is 0.03. So it becomes 4,000 divided by 0.03 e to the 0.03t. And don't forget, we have a 1/4 out front. And we're substituting in the values 0 and 4. Now again, maybe you already typed in your calculator 4,000 divided by 0.03. But I find it very helpful to write that step, because then you and everybody who looks at your work is like, oh yeah, you just divide by 0.03. That's how you take the integral of e to the nt. Now we can do all two of these computations at once. We have 4,000 divided by 0.03 times 1/4. So 4,000 divided by 0.03 times 1/4. That turns out to give me $33,333.33 repeating times e to the 0.03t, evaluated from 0 to 4.
0.
What? So first of all, is 33,000 the answer to the problem? Not even close, right? Nothing about this problem is $33,000. But we're about to multiply 33,000 times e to the 0.03 evaluated at 4 and 0. So now we have 33,000 with 0.3 repeating times parenthesis minus parenthesis, which is e to the 0.12 minus e to the 0. So that gives us 33,000 times e to the 0.12 minus e to the 0. Well, e to the 0 is just 1, so e to the 0.12 minus 1, which is 0.127468116 times the 33,333 point. How many 0.3333 should you type in? At least 10. There we go. $4,249.895. That rounds up to 0.90. 90 cents. Now, is that a reasonable answer? That's pretty reasonable. Pretty reasonable based on what we knew about the problem, somewhere between 4,000 and 4,500. So that's your average value of your account. Now, folks, now that we know that, why would you care? Like, under what circumstance would somebody say, hey, what's the average value of your account? Can you imagine anybody asking you that? Well, here's one answer. I don't know how quickly I can find this. But here's a bank, US Bank, just randomly chose one. And if you go into their different types of checkings and savings accounts, and here's an overview of their bank accounts. No, I just want to go to checking accounts. Why don't they have? Compare accounts. This is the benefits. Ways to waive monthly fee. So, in other words, when you open up a checking account with a bank and you want things like a checkbook so you can write checks or just the ability to use their checking account, normally there's a monthly fee. But if you don't want to pay the monthly fee, you can do certain things. So look, the way to have no monthly fee at all is to have $25,000 in combined personal deposits, credit balances with US Bank and or investments through US Bank Corp. So they want a combined total of $25,000 invested there, and then they won't charge you a monthly fee for a checking account. It's like, sure, let me just give you my $25,000 real quick. Well, the point is that's an average daily balance. So you might go up and down a little bit, but you're going to need an average of $25,000. Or look at this one, the easy account, no monthly maintenance fee with a combined monthly deposit, direct deposits totaling $1,000. So that's different. All you need is direct deposit. So when you get your paycheck from your job, just direct deposit all of your income, and then they'll waive your checking fee. The point is, one way to waive fees with a bank is to make sure that you have an average balance of at least a certain amount. Now, why do they care that you have at least $25,000 in their bank? Yeah, because they can use your money. Your money's not just sitting there. They've taken your money and they've invested it, and they're earning interest on it. And then with all the interest they're earning on your money, they're letting you use their checking account service. So there you go. Nice little. Yes, Bata. Bata?
What is the ED power of 0? Why the 4,000?
What is e to the power of 0?
Doesn't it the coefficient? Doesn't have a coefficient of 4,000 divided by 0.12?
Well, I did 4,000 divided by 0.03 times a fourth to get 33,000. Let me just look at your work. Oh, you're doing that whole thing. Yeah, and that's fine. So there's that part. And then over here, what's e to the 0? 1, exactly. So it's just, there's no e anymore. Cross it out. Scribble out that e. So yeah, you're right. It's going to be 4,000 over 0.12 times e to the 0.12 minus 4,000 over 0.12. There's no more e. All right. More question? All right, last question. This is number 10, and it says, if a cup of coffee has a temperature of 94 degrees in a room where the ambient air temperature is 24 degrees, then according to Newton's law of cooling, the temperature of the coffee after t minutes is 24 plus 70 e to the negative t over 51. What is the average temperature of the coffee during the first 30 minutes? They just said a lot of things, right? So first of all, how hot is 94 degrees Celsius? Do we know the conversion between Celsius and Fahrenheit? Fahrenheit is Celsius times 9/5 plus 32. Is that right? No. Is it 5/9? No. I think it's 9/5. Does anybody know? You know, what is it, Allison?
I said I can look it up.
Yeah, let's just look it up real quick.
Fahrenheit to Celsius.
5/9.
Yeah.
Fahrenheit to Celsius is Fahrenheit minus 32 times 5/9.
Yeah, right. So then the other way around.
Is Celsius times 9/5 plus 32.
Okay, great. That's what it is. Okay. So there's our conversion, folks. So first of all, let's just wrap our mind around what they're saying here. So first of all, what's the Fahrenheit degrees? Because fact is, we're Americans. Well, maybe not necessarily, but we live in America. We're all here in America, and in America we do Fahrenheit.
That's right.
Doggone it. Fahrenheit. We do Fahrenheit. So we know what Fahrenheit is, but we don't really have an intuitive sense for Celsius. Some of you might have an intuitive sense for Celsius because, you know, it's only the rest of the world that uses Celsius. So is anyone in here more comfortable with Celsius than Fahrenheit?
Yes.
What that is? Maybe others of you, I'm not sure. Yeah, okay, well, I use Fahrenheit. So Celsius, let's do it real quick. 94 times 9/5 plus 32. 94 times 9 divided by 5 plus 32. Okay, so that's actually 200 degrees. That is some hot coffee. Is that hot coffee? I think that's standard temperature coffee. If you work in a coffee shop, they typically heat coffee at around 190 to 200 degrees. If you go to McDonald's, watch out. Don't pour that coffee directly onto your lap because it's hot. Y'all hear about that lawsuit? Somebody spilled coffee on the lap and sued. All right, so 200-degree coffee, and now it's in the room, which is 24 degrees. So let's find out how hot the room is. So 9/5 times 24 degrees. So how hot is the room? 24 times 9 divided by 5 plus 32 is 75 degrees. Fahrenheit. All right. Well, we should all be so lucky to be in a room that's 75 degrees as opposed to 80. So now let's draw a picture of what's happening. Here's our graph. This is the temperature. And this is time. And let's see here. Well, we're going to have to stick with the Celsius in order to use the formula they gave us. But let's go ahead and mark in now. This is 24 degrees. And this is 94 degrees Celsius. So we can just remind ourselves, if it's helpful, that this is really 75 degrees Fahrenheit, and this is really 200 degrees Fahrenheit. There, I'm converting for us Americans. So, what's the 24 degrees? What's 24 degrees Celsius? The coffee or the room? The room. So this is our room temperature, and what was the 94 degrees? The coffee. Now, folks, you go ahead and tell me. We're talking about the temperature of the coffee. So if a cup of coffee has a temperature of 94 degrees, where the room temperature is 24 degrees, according to Newton's law of cooling, the temperature of the coffee after T minutes is that function. So let's start plotting out the temperature of the coffee. You don't have to draw this, but just watch what I draw. What is the temperature of the coffee going to do over time? It's going to decrease, right? I mean, what does coffee do? It gets cold. Well, how cold can coffee get? Can the coffee get that cold? That'd be pretty weird, right? If you set your coffee out and it actually got colder than room temperature, that'd be weird. So what's the coldest that a cup of coffee can become in a room? Room temperature. So we know that our curve is going to do something like this, where it's going to start out hot, and it stays hot for about 30 seconds, and then it starts cooling, but then eventually it's going to level off, and then it becomes room temperature. So does everybody believe that graph? That's what it's going to look like. Now that we've just figured that out in our head, let's just go back and see that it's called Newton's law of cooling. So Newton was sitting there in the late 1600s, early 1700s, and he was thinking about his cup of coffee, and he was like, hey, how does my cup of coffee get cold? And so he came up with a formula to actually track that. So here, let's graph that formula now. What was it, 24 minus 70 or plus 70? Plus 70, e to the power of negative x divided by 51. Now, what does my graph look like? Looks like a straight line, but why is that? And my axes are terrible. What should my y-axis be? Yeah, maybe up to just 100, right? Because we started off at around 94 degrees. Now, I'm not going out far enough because I can't see it leveling off. So now I need to take my x-axis. I'll start at time equals 0, and I'll go out, how many? Are they saying t is minutes? So how many minutes do you think it takes for your coffee to reach room temperature? How many hours does it take for your coffee to reach room temperature? 1 hour? So maybe I'll go out to 60 minutes. I'll go out to 2 hours, 120 minutes. So there's that. You know, I'll even go further than that because I'd like to see it level off. There. Can you see it leveling off? There it is. And did I type down that formula correctly? 24 plus 70 to the power of negative. Yeah, okay, I did. Okay. Well, there we have it. Now, first of all, let's see that horizontal asymptote, y equals 24. Is the cup of coffee approaching room temperature? Yeah. Is it ever going to reach room temperature? Well, maybe eventually. I mean, in theory, there's a little bit of energy in that coffee that maybe even if just one atom is bouncing around a little faster than usual. I mean, the model says it's an asymptote, that it never reaches 24 degrees. But practically speaking, it reaches 24 degrees. Now, let's change real quick. Was my graph correct at the beginning? Does it start leveling? Does it start level and then start to decrease? Or does it just immediately start to decrease? It just immediately starts to decrease, doesn't it? So there we have it. That's what our graph should actually look like. What's the most depressing part about your cup of coffee? How long does it take for it to be not very hot anymore? And not very long at all. You know, like, I don't know about you guys, but sometimes I get my cup of coffee, I'm like, boy, I'm going to sit here and enjoy this cup of coffee for the next 30 minutes. No. You're going to enjoy your cup of coffee for about 5 minutes. After that, it's not going to be hot anymore. Right? Isn't that sad? It's a little sad. Unless you have it in a thermos, right? Then it can stay hot. Okay, so now what? We've spent some time just kind of getting to know what all of this says. Should we be very impressed by Newton?
Yes.
Is this very impressive what he's come up with? You see us saying yes? I mean, is it really all that impressive? What did Newton come up with in all his brilliance? What's going to happen to the cup of coffee? It's going to cool off and approach room temperature. All right. Don't get me wrong, Newton was very smart, but this idea is not like earth-shattering. Okay, so now what are they asking? What is the average temperature of the coffee during the first 30 minutes? So that's it. Now that we've spent some time getting to know Newton's law of cooling, we want to know what the average temperature was within the first 30 minutes. So you see that, and then you draw your little dotted line, and you say, that's going to be my average temperature. So let's go ahead and find our average temperature. That's going to be the integral from 0 to 30 of 24 plus 70 e to the negative t 51st dt. And we have to put our fraction out front, 1 over 30 minus 0. First of all, any guesses on the average temperature between 24 and 94? What do you think it's going to be? Anyone want to throw out a number?
45.
45? Anyone else? We'll just go with Allison's guess. Okay. Thank you, Allison. Guess 45. Okay, well now let's actually find out. This is really 1/30th of the integral from 0 to 30 of 24 plus 70 e to the negative t for 51st. Now, what is negative t divided by 51? Isn't that negative 1/51st t? Maybe that's helpful to pull the fraction out so you can actually see the number, because we're about to divide by that number when you do an integral of e to the n t. So now what do we have? We have 1/30th of, well, sorry, there's a 24 here as well. That's 24t to the 0, right? 24t to the 0. So we have to take the antiderivative of that. That becomes 1/30th of t to the first divided by what you get. So that's 24 over 1 times t to the first. Plus 70 over negative 1/51st e to the negative 1/51st t, evaluated from 0 to 30. So, folks, it's a lot to look at, and you want to be very careful about writing it down. So what do we have now? We have 1/30th, 24t, plus 70 divided by negative 1/51st. Make sure you use parentheses. 70 divided by parenthesis, negative 1 divided by 51, parenthesis. That's negative 3570. So minus 3570 e to the negative 1/51st t evaluated from 0 to 3. So now we get to plug t into all that. Well, you know, we get to plug in 3 and plug in 0. So 1/30th of parenthesis minus parenthesis. So 24 times 3 minus 3570 e to the negative 3/51st minus 24 times 0, that's just 0, minus 3570 e to the 0, that's just 1, so there we go. The second part of that integral is a little easier. Look how misleading the calculation is while we're only halfway through. We're only halfway through the integral right now, and you see that big number, 33,570. Is that possibly the average temperature of the coffee? No, not unless you're suddenly drinking your coffee on the sun. Then maybe. So the numbers in the middle are, you know, don't look at those like they're the answer. We still have to do quite a bit of computation. So we have 1/30th. 24 times 3 is 72, minus 3570 e to the negative 3 divided by 51 is 3366.057. That was the first chunk. And then minus negative 3570. That's a double negative, so chop chop, that's a plus. And that gives us 1/30th of 72 minus that, which is negative 3294.057 plus 3570, which gives us 1/30th of 275.94, which still does not represent the temperature yet until we divide by 30. And that can't possibly be right. I got 9. Now we should all know that 9 degrees is not correct, right? So where did I go wrong? Instead of what? Verse 3. Oh, thank you. That is where I went wrong. That's 30. Silly me. That's 30. That's 30. Thank you. Ouch. Yeah, that's 30. So that changes quite a bit, doesn't it? But only at the very end. That changes a lot at the end. Hey, who caught that? Who said 30? Thank you, Michelle. Yeah, that was 30. Let's try that again. All we have to do is erase the last 2 lines of our work. So 24 times 30 is 720 minus 3570 e to the negative 30 divided by 51 minus 1982.44 minus, and that part is still negative 3570. So now we have 1/30th of 720 minus that, negative 1262. Oh, -1262 plus 3570, which is 1/30th of 2307.556, which is, oh boy, 76.9185. We'll say that. Is that Celsius or Fahrenheit? Celsius. So what is the average value of the coffee? 76 degrees. Now I'm sure you're all interested to know what is that in Fahrenheit. So 9/5 of 76 plus 32. That's times 9 divided by 5 plus 32. That's 170 degrees Fahrenheit. Which still sounds pretty hot, right? Does that still sound pretty hot? 170 degrees. I mean, that'd be hot if you were in it. I don't know if it's really that hot for a beverage. So now, the last thing we need to look at in this problem, take a look. Our coffee started at 94 degrees. The room temperature is 24 degrees. And we just found out that the average temperature is what, 76? So take a look, and we're going from, what, 30 minutes? Yeah, just 30 minutes. So I'm going to put in here x equals 30. So, can you all see the graph that we're looking at? Because I'd like us all to observe the graph. So what do we have here? This is the 94 degrees, which is the start. This is the 24 degrees, which is the room temperature. And then this is the 76 degrees, which is the average value. Right. So for 30 minutes, you're going to have your cup of coffee at an average of 76. Is that really fair, though? How long, or when, we should say, is your coffee actually 76 degrees? About when, over that 30-minute period, when is your coffee actually 76 degrees? Around 15 minutes? Is that all fair, folks, that this is 0 minutes and this is 30 minutes? Would you all agree that your coffee actually was 76 degrees at the 15-minute point? So half of the time, your coffee was hotter than 76 degrees, and half of the time, your coffee was cooler than 76 degrees. But we say your coffee was an average of 76 degrees because that's the average value. So would it be fair to advertise? Like, what if somebody was selling a coffee thermos and they said, special? Buy this coffee mug because it'll keep your coffee at an average temperature of 170 degrees, not dollar sign. There we go. So it'll keep your coffee at 170 degrees Fahrenheit. Now, first of all, do you need a mug to keep your coffee at 170 degrees Fahrenheit? Like a special thermos? No, because that's what room temperature is going to do anyway. If you just put your coffee in a paper cup in room temperature, it's going to stay at an average of 170 degrees Fahrenheit. So charging $30 for a special thermos, why would you bother spending money? Because that's, okay, but more importantly, how much of the time is your coffee going to be hotter than 170 degrees? How much of the time is your coffee going to be hotter than 170? Only half the time. And what's the other half of the time? Your coffee's going to be cold. Right? I mean, isn't this just terrible? Do you feel lied to by thermos companies? You know, companies that sell a thermos, they're trying to tell you that they're going to keep your coffee longer. And they might. I mean, to be honest, my coffee is still fairly hot. So, I mean, it helps a little bit. But that is what we're talking about, is how long can you potentially keep your coffee warm. So does anyone know how a thermos works? Why does it stay hot for so long? Because, touching this, it's not hot. So it's not heating up the whole thing. What's that? Yeah, how is it insulated? How is it insulated? You don't know how a thermos works?
No.
Okay, so in a thermos, you have the outside wall, which is cool to the touch, and then you have an extra inside wall, and what's filling that space right there is air. So there's a gap between the inside and the outside, and that's stopping the radiation of heat leaving the coffee. So because you've got this hot stuff right here, the heat doesn't pass well over the air, and so the outside of the cup isn't constantly radiating out the heat, and the heat stays on the inside. I don't know if I described that very well, but the point is it's double walled. So look for that when you buy your mug or your thermos. It's double walled. It's insulated with air or styrofoam. They could have put something else in there. Everyone, should we take a break? I think my phone went off a little bit ago. We finished section 3. Oh, my phone only went off a little bit ago. Yeah, the time is 12:02. Let's come back to 12:12.
Celsius and centigrade is the same.
What?
Centigrade and Celsius.
Yes, those are the same.
Oh.
folks. My goodness. I just flew right on past the end of our break. My goodness, and no one said, hey, Mr. G, hey, Mr. G, come on, let's get back to class. I realize that's my fault. Okay, so here we go, folks. We are all done with section 3.6, and taking a look at the board, we saw 3 unique applications of integration. Finding the area of a curvy shape, finding the volume of a 3D solid revolution, and finding the average value of a function over time. So we now get to start section 3.7, application to business, in which we are going to talk about supply and demand curves. Right? Supply and demand curves. So first of all, does everyone have section 3.7? I don't think everyone does. I sent them out a while ago, but maybe some people still need it. So who needs 3.7? Alexis? Allison, you? Steven, Josue? Sarai? Sadia, do you have it? Michelle? Perfect. Okay. Diego? Celia? Oops, that's the same one. Oh, sorry. Thank you. Alexis, did I even give you the right one? 3.7?
No. Wait, I don't know.
You need 3.7. Okay. Okay. All right. So folks, this entire last section is about supply and demand. And so before we start doing any of the problems, we want to make sure we really understand supply and demand and what we're talking about. So let's choose a product that we can all get excited about. So what should we be talking about? Should we be talking about pizza? Should we be talking about an iPhone? Should we be talking about a computer? Should we be talking about a car? A cup of coffee? What should we talk about?
Cheesecake.
Cheesecake? Is that what you said, Diego?
Yeah.
Cheesecake? Okay, well that's possible. We can talk about cheesecake. Anyone else have a?
Didn't they used to, isn't that one of the popular ones, like guns and cheese?
Yeah, guns and cheese. Yeah, guns and what else was it?
I don't remember.
Yeah, guns and butter. Guns and butter, I think that's what it was, yeah. So there are definitely a lot of things that we could talk about. So Diego had the courage to say cheesecake, so let's go with cheesecake. So first of all, folks, does everyone know what we're talking about when we say cheesecake? Here's a cheesecake, and you would cut it into many slices. There we go, how'd I do? There's our cheesecake, and where did we purchase this cheesecake? The Cheesecake Factory, of course. Because the Cheesecake Factory has really good deals. Well, not really good deals. Okay, it's expensive. But it's good, thick, rich, thousands and thousands of calories in this cheesecake. Yeah, I mean, thousands upon thousands. I mean, if you could only take one piece of food with you into the wilderness and survive for a week, take this cheesecake because it has more calories than your body can use. So, how much would you spend for a cheesecake, folks? $10, I've got $10. Now, I think for $10, any of us would buy an entire cheesecake. Or you can just make your own, that's fair. But like, for instance, if you go to Starbucks or Barnes & Noble, they sell cheesecake, you can expect to pay $4 for one slice of cheesecake. And if a cheesecake comes with 1, 2, 3, 4, 8 pieces, 8 times 4 is 32, I mean, you're spending $32 to buy it by the slice. So I think $10 would be a very, very inexpensive cheesecake, like something from the freezer section of the grocery store. How much could you really reasonably spend, you know, at a coffee shop or a boutique pastry shop or something like that? Could we say maybe more like $20? Is that fair? $20? So we're going to say $20 is maybe the average value. 10 would be cheap, and 30 would be expensive. But let's go one step further. What if you could buy a whole cheesecake for $1? First of all, how many of you would go ahead and buy a cheesecake right now for $1? I mean, everybody, right? It's such a good deal. How can you say no? You're like, I don't even need the cheesecake, but for $1, I'll buy it and give it out to people. Now, what about $100? How many of you are going to buy a cheesecake for $100? What, Celia? Yeah, better be made of gold, right? I mean, $100 right out. Well, see, this is the spectrum that we're talking about. So let's go ahead and look at our demand function. here's our demand function. So let's talk about our demand function first. Everybody just draw this graph somewhere on a piece of paper. You can do it in the upper right of this packet if you like. So there's our demand function. Remind yourself that, well, should I start over? No, I want to draw on this one. You just have to draw it. So our x-axis is Q for quantity. How many are you going to sell? And our y-axis is P for price. How much can you charge? So the kind of weird thing about a demand curve, in my opinion, is that you start at the y-axis and then look at the x-axis. So for instance, here's our price where $100 for a cheesecake priced everybody out of the market. How many people bought a cheesecake for $100? How many people bought the cheesecake for $100? Zero. Right? So if you set the price at $100, boom, no one's going to buy your stupid cheesecake. Now, however, apparently just by reducing the price to around $90, how many people buy your cheesecake? A couple. Some people. You know, maybe they were just trying to support you. Maybe it was your grandma. Maybe it was somebody nice. Or maybe it was gold leaf cheesecake. Who knows? But you lower the price, you actually got some people to come buy it. The point is, let's just say 5 people. Let's say 5 people were actually willing to buy that cheesecake for 90 bucks. First of all, I'd like to meet those 5 people because I got more things to sell them. Okay, so now what? We lower the price again to $80. And how many people? 10. 10 people buy it at 80 bucks. Great. Now what does that really mean, folks? Let's analyze this for a second. 5 people were willing to buy it at 90 bucks. So now consider the 10 people who bought it for 80. Doesn't that 10 include the 5 people who would have been willing to spend 90? Right? Because if I put it on the market at 80 bucks, I'm going to get the people who are willing to spend 90. But they're like, woohoo, it's only 80. Right? So for those 5 people who are willing to spend 90 bucks, the fact that I set my price at 80 bucks, those 10 people that showed up to buy it includes the 5 people who would have spent 90, but 5 more people who were only willing to spend 80. Okay? This is very important. Let's say we go down to 70 bucks. Now 15 people show up to buy my cheesecake at 70 bucks. What does that mean? Who are those 15 people? 5 of them were the people who were willing to spend 90 bucks. Another 5 of them were the people who were willing to spend 80 bucks, and 5 of them were just those people who were willing to spend 70 bucks. So, at least according to this model, we're getting 5 more people out of the woodwork every time we lower the price by $10. But really, if you look at that 15, yeah, that's 15 people who are willing to spend 70, but some of those 15 people are willing to have spent more. They would have paid more. All right? Well, that's it. That's our main idea here, is that as we look at this demand curve going down, and now let's look at what actually happened. Who knows what this special point is right here, where you've got the demand curve and the supply curve? What happens right there? What's that point called where supply meets demand?
Equilibrium.
Equilibrium. That's the equilibrium point. And the whole point of capitalism, as opposed to socialism or communism, is that the invisible hand of capitalism chooses the price for the market. Because what you do is you just look at the supply curve and the demand curve, and wherever they meet, that becomes the price that the market uses. So that then becomes the actual equilibrium price. So how much was that then? At least according to my graph, can we agree that that was $50? What do you think? Can we say that that was 50 bucks? So at $50, we actually ended up with, at least according to this model as I'm drawing it, 25. So at a price of $50, that was the equilibrium. That's how much we're actually going to sell this cheesecake for, which is like way more than what we were originally talking about. This is just where the numbers went. But the point is, at $50, how many people showed up to buy it? 25 people. Now, out of those 25 people, how many of them would have spent more? 20 people would have spent more. Only 5 people were willing to spend, only 5 people were like, nope, 50 is my most. But 20 of those 25 people would have spent $60. Okay? So, now let's think about what this means. Everyone done thinking? Just kidding. Okay, let's keep talking. So the point where the demand and supply curve cross is called the equilibrium point. That's how much we actually do charge. So now let's look at this idea. Let's read this out now that we're ready to talk about it. Suppose that the price is set at the equilibrium price so that the quantity demanded equals the quantity supplied. That's always what we want. The quantity demanded equals the quantity supplied means that the warehouse where they're selling it, they're not going to sell out and they're not going to run out. You will have exactly the number of customers show up to buy exactly the number of products that you have. That's a good deal because you don't want to end up with extra products sitting on your shelf gathering dust, and you don't want people showing up saying, hey, I want to buy one, and you're like, sorry, I ran out, because that's bad press. So that's why the equilibrium price is important, because that's the dollar value such that a store will exactly sell out of their goods, no more, no less. Okay, now think about the folks who are represented on the left of the equilibrium point. Who were these people to the left of the equilibrium point? Who were these people? They're customers, yeah. And they're the people who would have been willing to pay more. Okay? So these are the people would have been willing to spend more. And you probably aren't, I don't know if you feel that way about cheesecake, but can you think of a product in your own life where you're like, awesome, I got this at a deal, I would have paid more? I mean, that happens almost every time I go to the grocery store. My favorite popsicles are on sale for $3. I'm like, I would have paid $4. Right? So what is it like to be these people? What is it like to be a person who would have spent more? How do you feel if you would have spent more, but you only had to pay less? How do you feel about life? Yeah, you look good, you feel good, you're feeling happy, right? Because as far as you're concerned, you spent less than what you were willing to pay. That means you feel like you got it at a discount, right? So all these people, how are they feeling? Feeling good. Right? They're happy. They're very happy. So let's keep going. The consumers on the left would have been willing to pay a higher price than they ended up having to pay. So the equilibrium price saved them money, didn't it? The equilibrium price actually saved them money. They would have spent more, but the equilibrium price is so low, I just saved money. Now I have money in my wallet that I didn't spend. So now I'm even more happy. Not only did I psychologically perceive that I got a good deal, but I actually have extra money left over in my wallet. How much money do I have left over in my wallet? Exactly right. How much money do I have left in my wallet, in my bank account? The amount of money I would have spent but didn't have to. On the other hand, okay, so let's stop right there. The amount of money that's in my pocket that I would have spent but I didn't have to, that's called consumer surplus. So everybody draw a horizontal line right here. And this area right here, this area is called consumer surplus. Consumer surplus is defined to be the amount of money consumers would have paid, but they didn't have to. And isn't that wonderful? It's wonderful. It's a wonderful concept. It's a wonderful idea. It makes everyone feel good. Wait, it makes everyone feel good. Yeah, so that's called consumer surplus. The money we would have been willing to spend, but we didn't have to, and now I have all that money sitting in my wallet, burning a hole in my pocket. I can go out and buy something else. Which hopefully I buy that something else also at a cost less than what I would have been willing to spend. And that's a little more money I have left in my wallet. All right? Okay, we've just taken the perspective of the consumer. It is possible to have a consumer surplus, money they would have spent but didn't have to. So now let's talk about the producer. Let's talk about the producer now. So the supply curve. Here's our supply curve. Okay. Now, how many, if the price is 0, everybody, we're starting all the way over again from scratch, and now we're talking about producers. If a producer can only charge $0 for a good, how many are they going to produce? Nothing. I'm not going to give anything away for free. You think I'm going to do any work at all to make a shirt and then just give it away for free? Why would I do that? That makes no sense. So on the supply curve always goes through 0, 0. Because if you can charge $0, I'm not going to make anything. Okay, but on the other hand, let's say that the producer can charge at least $10. Okay, so they can charge $10. How many products are they willing to make? Oh wait, sorry, these numbers are all different now. Oh no, these are the same numbers. So they get to charge $10. How many products are they willing to make? A few. Maybe this time they'll make 5 products. They're like, hey, for $10 each, it's worth my time, I'll make 5 and then call it quits. What if they can charge even more than $10? What if they can charge $20? Well, now they're willing to supply even more. They're like, hey, charge 20 bucks or sell for 20 bucks. I'm making more profit. I'll go ahead and put time into making more of them. And so on and so forth, right? So the more money they can charge, the more products they're willing to make because they're making more profit from each product and it's worth their time to do so. Until finally it gets to the point that they can charge $50 and they reach equilibrium. Okay? Now let's ask the same question. What if you're the producer who was willing, you were only willing to sell 15 products if you got to charge $20. So if you only got to charge $20, you were only willing to sell 15 products. But all of a sudden, you got to charge $50. But imagine how cool this is, okay? All I did was I sit around and I made 15 t-shirts. I made 15 t-shirts. Okay, I'm in the t-shirt business. And I was gonna charge 20 bucks. Okay, that was my whole business model. I made 15 t-shirts, I'm gonna charge $20. But wait, the equilibrium price was set at $50. So what does that mean to me as the business owner? I was only gonna charge 20 bucks, but the equilibrium price is 50. I get to charge 50, and are people gonna show up to buy it? Yeah, they are actually, because it's equilibrium price. If it's equilibrium price, people are gonna show up. So this is amazing. How am I feeling now as a producer? I was only gonna charge 20, but I got to charge 50. What just happened? I made a lot more money than I expected, right? So now, as a producer, every point on this curve represents a point where I would have only charged 10, but I got to charge 50. Or here, I would have only charged 20, but I got to charge 50. Or here, I would have only charged 30, but I got to charge 50. And here, I would have only charged 40, but I got to charge 50 because I'm using the equilibrium price instead of the price that I personally would have charged. So then, what does all this shaded area represent? It represents money I earned by charging the equilibrium price, even though I didn't even want that price. I would have charged less, but I got to charge more. And so what does this represent? Extra income. Oh, well, it represents extra income. First of all, it's money that I earned because the equilibrium price earned it for me, even though I would have been willing to earn less. So let me put that over here somewhere. So, would have been willing to earn less. Is that fair? I would have been willing to earn less. But I earned more because of the equilibrium price. And how are you feeling as a company? As a company, you're feeling pretty good. You're super excited. You're making more income than you personally would have required. You know, I was only going to charge 20 bucks for a t-shirt, but the equilibrium price is 50, so I'm going to charge 50. And so we call this producer surplus. So the consumer surplus is the money that I didn't have to spend because the price was lower than I would have spent. And I feel good because I still have money in my pocket. And producer surplus is the extra income companies earned because they got to charge the equilibrium price even though they would have been willing to charge less. See that?
So if the price stays at 50, then the quantity still increase?
If the price stays at 50, why would the quantity increase?
Like, why stop? t-shirts?
Well, right, I mean, that's the equilibrium. There are only 25 people in the market willing to pay that price. That's what these curves mean. These curves represent, this demand curves represents the number of people willing to buy a product for that much. So in the market, there's only 25 people willing to buy the product at 50. So if you keep it at 50, the quantity won't change.
But if I decrease what they're paying.
Oh, if you change the price? Well, if you arbitrarily change the price down to like 40, it would no longer be the equilibrium point. You'd have people over here and people over here. If you lower the price to 40, you would only have 20 producers willing to produce. But you would have 80 people wanting to buy. So if you only have 20 products and 80 people showed up to buy it, what would happen? Yeah, you'd run out. And you'd have 60 very unsatisfied people who are like, oh darn it, they ran out. I couldn't buy what I wanted. Okay, good. All right, boy, oh boy, I sure did fill that screen with a whole lot there, so now let me just erase everything. Now, we just learned two concepts. And it's very important that you're able to describe this to yourself, folks, okay? So now look again. This triangle of area that exists below the demand curve, but above the equilibrium price, okay? That represents the consumer surplus. This pen is terrifying. Why do I keep using it? That represents the consumer surplus. And what does that represent again? What? This consumer surplus. How would you describe that to a friend?
The triangle below the demand curve.
Well, that's true. It is the triangle below the demand curve and above the equilibrium price. I mean, what does it feel like as a consumer? What does it actually mean about me and my wallet? It's what? Yeah, it's money I still have in my wallet because I would have spent more, but I didn't have to because the price was low. That's what consumer is. Consumer surplus is all the money I still have in my wallet because I would have spent it. Had they charged more, I would have paid for it. But the price was low, so I got to buy my product and keep some money for myself. So this is money in my pocket. So I'm going to say that. Money in my pocket. Okay, now what about producer surplus? What is the area, what does the area represent above the supply curve, but below the equilibrium curve? So the area above the supply curve, but below the equilibrium curve, that's the producer surplus. What is that?
So you would have been willing to earn less.
Right, you would have been willing to earn less, but you earned more. And so producer surplus is extra income. It's extra income. Extra income for the company. It's like, wahoo, I got to earn more than I thought. I mean, just imagine if you showed up at a bake sale with cookies. All right, everyone, have you done a bake sale before? You just sat at home last night, you made a whole bunch of cookies, and you're going to charge $3 per cookie. But you show up at the bake sale, and everybody's charging $5 per cookie. Now, what are you going to do? Are you going to keep charging $3 for your cookies? Or are you going to be like, everyone else is charging $5, I'm going to charge $5. Right? And so that's extra income. What's the other?
I would charge $4.50.
Oh, yeah, there you go. Charge $4.50. Yeah, that way more people are going to buy your cookie. Okay, now, either way, doesn't this paint kind of a blissful picture of society? You're like, geez, capitalism is great. All these consumers have extra money in their wallets. All these business people are making more income than they thought they would. I mean, this sounds like a utopia. And it's only kind of true, right? Because there's only so many people who are going to buy that $90 cheesecake, right? And there's only so many people who are going to buy that $70 cheesecake. And so all we're really talking about is that just those people who would have spent more got to keep their money. Did me, the average American, get to keep any money? No, because the equilibrium price was actually right at the sweet spot of what I was willing to pay. So really, who has the consumer surplus?
Rich.
Yeah, fairly super rich people who would have been willing to pay $90 for a cheesecake, right? And then who really has the producer surplus? Companies who can manufacture their product, no, wait, companies, yeah, that can manufacture their product and sell it at a low price. So that would be like pretty good companies. Companies who are efficient, capable of turning out a product at a low price, and yet they're going to charge more, so they kind of luck out. All right, well, folks, we've done it. Did we finish reading this paragraph? On the other hand, the producers represented on the left would have been willing to supply these goods for a lower price, but they made more money than they expected to. Both of these groups ended up with extra cash in their pockets. Anyway, this should definitely be a lesson that they teach in Capitalism 101. Be capitalist. Here's one really good reason to be capitalist. Okay. Yep. Now keep in mind though, is there anybody willing to buy a $90 cheesecake that's going to buy a $20 cheesecake? No. You know what that person's going to do who wants a $90 cheesecake? They're going to find a fancy cheesecake store that actually sells cheesecakes for $90. Right? That's how the market works. I mean, is a millionaire going to buy a Toyota Corolla? No, they're going to go out and they're going to end up spending their money on their Lamborghini or Ferrari or whatever they want, right? I mean, it's not very often that you have somebody who's willing to spend $100,000 for a car, and they're like, I'll take the Corolla. Right? So now that we just spent all this time investigating the idea of consumer surplus and producer surplus, are there really a lot of people willing to buy $90 cheesecakes that are buying $20 cheesecakes? Not really, because they're just going to go to an expensive cheesecake store. That's the whole point of having upper-end things, you know, high-end products, because there are people in the market willing to buy it. It's just like a pair of jeans. I would like to buy a pair of jeans for 15 bucks. Thank you very much. That's about how much I want to pay for a pair of jeans. But I know people who spend $50 for a pair of jeans. And I'm like, are those jeans magic? Right? Now, if anyone in here buys a pair of jeans for $50, that's fine. I just don't want to spend $50 for a pair of jeans. I'm willing to spend money on other things like air conditioning. I don't mind having a really high air conditioning bill because then I'm comfortable. Okay, enough said. Here we go, folks. Now, did you all notice that in order to calculate consumer surplus, we just have to find an area? And to find producer surplus, we just have to find an area. And therefore, we're about to do integrals. So that's it. We're about to do some integrals. Now, I only have 5 minutes. That's just enough time for us to write down some formulas. So let's write down some formulas. Let's do this by making a nice little formula sheet. You can either do this on a sheet of lined paper, or you can do it just somewhere on that piece of paper on the right-hand margin. So on the right-hand margin, let's draw this out. What we have, this is just your formula, so start a new drawing. We have a demand curve and a supply curve. So this is D of X, and this is S of X. Turn that up. Yep. And we have our equilibrium point, which has a X value and a Y value. And we're going to call, remember this is quantity, and this is price. And so our equilibrium point is the coordinate Q star, P star. They just use that notation in the textbook, so I'm going to use that notation. So Q star is the equilibrium quantity, P star is the equilibrium price, which is the price that the market is actually going to charge and the quantity of products that it's actually going to sell, no more, no less, because that's the equilibrium. Now, we draw a horizontal line to find the area, consumer surplus, and then to find the area, producer surplus. So graphically, we are simply finding the area of this triangle and this triangle. It's not always going to be a triangle. These curves might be curvy, but they look rather triangular-ish, right? So now let's write down our formulas. Consumer surplus, remember, is this triangular area up here. So it's the area underneath the demand curve, but above the equilibrium price. And so formulaically, it turns out to be the integral from 0 to Q star. After all, that's how far we're doing the integral. We're going from 0 to Q star, that's our integral. Of the demand curve, first of all, I'm going to do dx so quick. Demand curve, oh no, we should do Q. demand curve, dq, minus, now what are we're doing this top curve, minusing, well, we just want to find the area of that triangle. And so the way we do that is we find all the area underneath, but then we subtract out the area of this rectangle. So I just want you to imagine, if you want consumer surplus, find all the area under the curve, but then subtract out the rectangle. Does that make sense? You have a rectangle here under my hand. So if you find all the area below the demand curve, but then subtract out that rectangle, you'll be left with just the triangle up top. So what is the area of this rectangle? The area of a rectangle is just width times height. And the width is Q star and the height is P star. So we're going to subtract out the area of that rectangle, P star, Q star. And that will give us just the area at the top. That's consumer surplus. We take the integral of the demand curve to find all that area, but then we subtract out the area of the rectangle underneath it, and then that gives you just the consumer surplus. That's one formula. The other formula for producer surplus is we go just the reverse. Now I want just this area. So now what I'm going to do is find the area of the whole rectangle. So find that whole rectangle there, and then subtract the area under the supply curve. So if I want that triangle, I do the whole rectangle, and then I subtract the area under the supply curve. So I find the area of the whole rectangle, which is P star, Q star, and then subtract the area under the supply curve. I think that's as far as we're going to get today.
I don't think we're actually going to do a problem. No, we're not.
But I hope that the picture I painted for you makes sense now, at least conceptually. You know what I would do if I were you now is go back, reread the textbook. Notice how I say the phrase, reread the textbook. Reread the textbook for this section to see what they say about it. Rewatch the videos. Notice how I say rewatch the videos for this section so that you can really get a good understanding of consumer surplus and producer surplus. And even just Google it and look at the Wikipedia page, or look at anything else on producer surplus and consumer surplus, so that the concept is solid in your mind. Because then all we're going to do is just calculate some integrals and we're done. Okie doke.